Hello everyone. Today we have an exciting topic on the derivative of exponential functions. So we're going to go ahead and get right into it and talk about the rules and do a lot of practice. So just a quick review of exponential functions. Of course, we want to take a look at what the graph of an exponential function looks like. So if I graph the function e to the x, okay, it looks something like that. All right, and we know, of course, that it's going to cross at this point here, which is going to be 0, 1. And why does an exponential graph cross at the point 0, 1? Well, that's because of the fact that e to the 0 always equals 1. So if this is the graph e to the x, then when I'm crossing at when x is 0, then e to the 0 is going to be 1. So this is an essential fact that you want to make sure that you memorize and remember from your years past, that anything to the 0 power is 1. Okay. Some other things about the exponential graph that you want to make sure that you recall is that its domain is all real numbers, so negative infinity to infinity. Okay, that you can put any value in for x and you will get an output. If you put negative values in, you get very small decimals. If you put positive numbers, the larger that positive number, the higher this graph is going here in this direction. And so we can get very, very large numbers. Okay, our range, though, is restricted. Our range, no matter what how small the number is that you put in for x, you will never get to 0 or smaller than 0. And so we say that we have an open interval 0 to infinity would be our range. That you can see that it will never touch or cross the x-axis here. Okay, and so we say that it gets infinitely close to 0 but does not touch it. And obviously as we move to the right, that it goes higher and higher to infinity. We can also talk about the limits as x approaches positive and negative infinity of the function. And just looking at the graph, you can see here that as x approaches negative infinity, the far left-hand side of the graph, what height is the graph leveling off at? And because of the range and because of what we just talked about, we should be able to see that 0 is in fact the limit as x approaches negative infinity. But the limit as x approaches infinity of the function e to the x. So now we're talking about moving to the right-hand side of the graph, okay? And where is that going? Well, we can see it skyrocketing higher and higher, and so we would say the limit would be infinity. The last thing that you might want to be reminded of is that e is a number, and e is approximately the value 2.718. It's an irrational number like pi. When used as the base of a logarithmic function, so log base e of x, we would say that that is called a natural log, so natural log of x. All right, so our natural log function has a base of e. It is a very commonly used function in many different applications in science, and so for that reason we don't put the e there, we just give it its fancy name, natural log of x. And hopefully you can recall, of course, then that because the base is e, if I took the natural log of e, I would get 1. So those are some important kind of facts about the exponential function, about its graph, about its domain and range, and of course just about the properties of e. So we're going to move on now and get the rules for how to take the derivative of an exponential function. Okay, there are 4 main rules that we are going to talk about, and you'll see as we go through these that they actually, all 4 of them, have so much in common, and they all kind of blend together. The basic first 2 are, first of all, if you take the derivative of e to the x. So if I take the derivative of just e raised to the x power, it is simply going to just be e to the x. Okay, so the derivative of e to the x is e to the x, which is a nice easy one to start with. All right, what if we take the derivative of an exponential function where the base is something other than e? So if I take it, and now that base has to be a constant, as I wrote here, okay, a has to be a constant, a has to be a positive number, and a cannot be 1. Because if a is 1, Well, 1 to anything is 1, okay? And so we take the derivative where a is a constant other than 1 and is a positive number. So when we do that, what is the rule for that? Well, you'll see that, again, it's a to the x, but now you have to multiply that times the natural log of the base. And the reason why we didn't have to do that in the first rule is because we just reviewed what happens when you do the natural log of e. Well, you get 1. And so in essence, we really did do rule number 2 with rule number 1. But we did e to the x, natural log of e, but natural log of e is 1, and so it just goes away. Okay, so those are the first 2 rules that you need to memorize. Now, what happens when you have an exponential function where your exponent is a function in terms of x? Well, then we kind of note it like this. We say d dx of e to the u. Okay, and remember, u is a function in terms of x. So to take the derivative of this, we do e to the u, so we copy what we're given, times the derivative of that function in terms of x, the derivative of the exponent. So e to the u du. Okay, if we have a exponential function with a base other than e, again, a is a constant greater than 0 and not equal to 1, okay, and our exponent is a function in terms of x, what do? Well, it's going to be a to the u times du, so the derivative of that exponent, times the natural log of the base. Okay, so there you have it. There are 4 basic rules of taking the derivative of exponential functions. It's essential that you memorize these 4 rules and know them. We're going to go ahead and practice using them. What you're going to find is that if you memorize these simple rules, the application of them in these examples that come up is really not that difficult, because all we're going to do is rely back on our original rules of differentiation of product and power and quotient rules. So here we go. Let's get started on some examples. Okay, we're going to go ahead and take the derivative of each of these different examples. So the first one, f of x equals e to the 3x squared minus 5x. All right, so I have a base of e. When I take the derivative, I simply copy my exponential, then times the derivative of the exponent. So in this case, the derivative of the exponent would be 6x minus 5. Now I want to make sure to put that in parentheses, and that's it. That's as much as you need to do with that derivative. All right, so let's look at the next one. F of x is e to the x times x squared. So I would definitely say, as I look at this, that that's a product. And if I have a product, I need to go ahead and use the product rule when I figure out my derivative. Okay, so if I use the product rule, remember it's first, which is e to the x, times the derivative of the second, which would be 2x, plus the second, which is x squared, times the derivative of the first. Well, derivative of e to the x is simply e to the x. And so we could do one more step if we wanted to and go ahead and factor out the e to the x, and we'd be left with 2x plus x squared. And that's the derivative of e to the x squared. Okay, our third example here is f of x is e to the x sine 2x. And so we definitely have an exponential, and then our u here, our exponent, is a function in terms of x, and it involves a product and also a chain rule. So we have a lot to kind of figure out here. All right, so when we do the derivative, the rule is e to the u, so we copy this down, times the derivative of that exponent. So the exponent here is x sine 2x, which we said is a product, so it's going to be first, times the derivative of sine 2x would be cosine, keep the angle, times the derivative of the angle would be 2, plus second would be my sine 2x, times the derivative of x is just 1. All right, so if I kind of just rewrote that one time, just to clean up the inside here, I would say that I have 2x cos 2x plus sine 2x. Okay, and that is the derivative of that given function. All right, number 4. Number 4, we have our first example here where we have a base other than e. So remember, when we take the derivative of that, We still copy down what we're given, 3 to the 2x. Then we take the derivative of the exponent, so the derivative of 2x is 2. And then we're going to take the natural log of our base. Okay, that answer as is a perfectly fine answer. And sometimes in multiple choice it might be given like that, but more often they might try to simplify this down using your log rules that you might have forgotten from last year. So if you remember, just in this piece right here, okay, if we have a number in front of a log, there is a log rule called the power rule that tells us that we can go ahead and put that 2 up here as an exponent on that 3. And so if I rewrite this, I could rewrite it as f prime of x is equal to 3 to the 2x times natural log of 3 squared. Or, of course, 3 to the 2x natural log of 9. And so that might be the way that if it was multiple choice, that they might clean that up. And so I'm just encouraging you that if you get an answer and if it's multiple choice and you're pretty confident that you know the rule and you did it right and your choice isn't there, you might want to just look back through and in fact realize that they might have used some log rules to clean it up, just that extra step. All right. Okay, the last of these kind of simpler examples that we're going to do is asking us to find the derivative of f of x equals cos of 2 to the pi t. So, all right, this time our exponential is buried within the angle of the function, okay, of the cos function. And so we're going to go ahead and follow our chain rule when we have a trig function. We're going to take the derivative of cosine, which is, of course, negative sine. We're going to keep the angle, 2 to the pi t. Then we're going to take the derivative of the angle. And when we take the derivative of the angle, here's where the exponential, the new rules, come in. So we copy down what we have, 2 to the pi t, times the derivative of the exponent. Well, the derivative of pi t, remember pi is a number, and so the derivative of pi t is simply pi, times the natural log of the base, so 2. All right, and so that is the derivative. And again, you could take one more step and clean up if you recognize that this pi here could be put as an exponent using your natural log rules. So times natural log of 2 to the pi. Okay, the next example asks us to write the equation of the tangent line to f of x equals 6 to the x minus 3 at x equals 3. So, of course, we have had so much practice with these. If we want to write the equation of a tangent line, we need two things, of course. We need our point and we need our slope. So our point comes from the original function, plugging in the x value and getting out a y value. So if I said f of 3, it would be 6 to the 3 minus 3. And so 6 to the 3 minus 3 is obviously 6 to the 0. So 6 to the 0 is 1. And so we would say our point here would be 3, 1. All right. And now we need our slope. So our slope obviously comes from the derivative. So we're going to take the derivative of f. All right, and so exponential function with a base of a constant other than e, we're going to go ahead and copy that, 6 to the x minus 3 times the derivative of the exponent, which would just simply be 1, times natural log of the base. And so if I take this and go ahead and plug in my 3 to find the slope at 3, it'd be 6 to the 3 minus 3 would be 0. Times natural log of 6. Well, that is just going to give me a slope of natural log of 6 because of this, of course, is 1. And so our slope is natural log of 6 and our point is 3, 1. So we're ready to write the equation of the tangent line. It would be y minus 1 equals natural log of 6, x minus 3. And that would be the equation of our tangent line at x equals 3. Okay, last one we're going to do is given the function f of x equals x e to the negative x, find intervals of increase and decrease, x coordinates of any relative extremas, intervals of concavity, x coordinates of any points of inflection. So kind of taking back everything that we've just been doing recently, but now we're going to do it when we're given an exponential function to start with. All right, so if you think through, if we need intervals of increase and decrease and x coordinates of any relative extrema, hopefully we're thinking, oh, that's my first derivative. So in order to find any of those, we need to go ahead and find our first derivative and find our critical points. So we're going to go ahead and take the derivative of the given function. Now my given function here is a product, x times e to the negative x. And so I'm going to use my product rule as I go ahead and take this derivative. So first times the derivative of e to the negative x. Well, that's e to the u, so I'm going to copy down e to the u times the derivative of the exponent would be negative 1 plus the second, so e to the negative x, times the derivative of x would just be 1. Okay, if I wanted to clean that up just one step, I could notice that both the left hand and the right hand side of my plus sign have an e to the negative x. And so I should be able to go ahead and factor that out. So e to the negative x gets factored out, and what's left behind is a negative x plus 1. And so if I want to find my critical values, I am setting then each of these factors equal to 0. So I have e to the negative x equals 0, and I have negative x plus 1 equals 0. Okay, the first part of this question is interesting. E to the negative x equals 0, and this is why it's important that we kind of spent just a couple minutes reviewing the exponential graph. When we looked at our exponential graph, we noticed that our function looked like this. Okay, and what that told us is that the graph got infinitely close to the x-axis, infinitely close to 0, but would never ever touch it. And so if that's the case, e to the anything, will it ever equal 0? No, it will not. And so if you are ever asked any exponential, when is it going to equal 0? The answer is going to be it's not, does not exist. So the left-hand side of your function here, of your derivative, is not going to yield any critical values. So we're only really relying on the right-hand side, this negative x plus 1 equals 0. So if I add the x over, I would end up with, of course, 1 equals x. And so there is my one critical value that then I can go ahead and make my number line, my sign chart for. Okay, so I'm going to make a sign chart with f prime and f. I'm going to put 1 on it. That's going to be my 0. Okay, now I'm going to test a number to the left and to the right. And of course I'm testing it back here in my first derivative. So when I test in 0, e to the negative 0, which is just e to the 0, well, that's positive because that's going to be 1. And then negative 0, which would just be 0 plus 1, is also positive. So I would definitely say a positive times positive is a positive, and the function is going to be increasing before 1. Okay, after 1, so let's pick 2. E to the negative 2. Now don't let that negative confuse you. Remember, a negative exponent does not give you back a negative number. A negative exponent just gives you back a very small decimal. So e to the negative 2 is a positive decimal. Okay, now negative 2 plus 1, however, is negative. So a positive times a negative is a negative, meaning you're going to be decreasing after 1. Okay, so we are ready to say that we are increasing. The f is increasing from negative infinity to 1. And that was because f prime was greater than 0. We are ready to say that f is decreasing from 1 to infinity. And that's because f prime was less than 0. We also can say that we have a relative maximum at x equals 1 because f prime changes from positive to negative. Okay, the second part of this question asks for the intervals of concavity and the x-coordinates of any points of inflection. So, of course, we get that from the second derivative. All right, so I already have the first derivative. I'm ready to go ahead and take that, take its derivative again to get the second derivative. Okay, so second derivative is equal to. Again, we have a product. And so e to the negative x is our first. So we copy that down. Times the derivative of the second. The derivative of negative x plus 1 would simply be negative 1. Plus, copy down my second, negative x plus 1, times the derivative of the first would be e to the u, times the derivative of the exponent, which is negative 1. Okay, so if I take a look at this, I can definitely notice that I have an e to the negative x on both sides of my plus sign. I also have this negative 1 on both sides. So I'm going to go ahead and factor out a negative e to the negative x from both sides. And so what would be left behind? Well, on the left-hand side, that cancels everything out, so it's just a 1. Okay, and then plus, on the right-hand side, this is completely going to be gone. And so all that's left is this negative x plus 1. So if I clean that up, I get negative e to the negative x. 1 plus 1 is 2 minus x. Okay, so that is my second derivative, which of course I need to set equal to 0 and make my t-chart. So each of the factors again get set equal to 0. So I have 0 as equal to negative e to the negative x, and I have 0 equaling 2 minus x. Okay, on the left-hand side, as we talked about, anytime it's asking for an exponential to equal 0, we were going to say it does not exist. Okay, on the right-hand side, I'm going to go ahead and add my x over, and I would just get x is equal to 2. Okay, and so I have my critical value of x equals 2. I'm ready to make my sign chart for the second derivative. Okay, so second derivative, and I'm going to put my 2. All right, and now I need to go ahead and test values to the left and to the right of 2 into the second derivative, which of course is right here. All right, so if I test in a 0, I have negative e to the 0. Well, that's negative 1, so it would be negative times 2 minus 0 would be 2, which would be a positive. So negative times a positive is a negative, which means we're going to be concave down. Okay, after 2, so let's plug in a 3. I'd have negative of e to the negative 3. All right, so e to the negative 3, we said, was simply just a very small decimal. But the fact that we have the negative out front here tells us we have the negative of this positive value, and so therefore we're going to have a negative times a 2 minus 3 would be negative, so negative times a negative would be a positive, which means I'm going to be concave up here. All right, so we can definitely see that we have an interval of concave down and concave up, and so therefore we also have a inflection point at x equals 2. So I'm ready to make my conclusions. I can say that I'm concave up from 2 to infinity because the second derivative is greater than 0. I can say that I'm concave down from negative infinity to 2, and that's because the second derivative was negative. I can also say that I have a point of inflection at x equals 2 because the second derivative changes sign. Okay, so hopefully that was some good review. Again, just kind of pulling in the new rules for taking the derivative of exponentials, but also reviewing so much of what we've been doing recently with the intervals of concavity and increase and decrease, and just kind of tying everything together. Okay, I have one more thing for you, and then we're going to be all done with this video. Okay, the last thing we're going to do is I have 6 examples here that all kind of look very similar, but we want to just make sure that we recognize when do we have an exponential function, when do we not, and make sure that we're applying the rules for our exponential functions only when we have the exponential function. All right, so we're just going to go ahead and find y prime given each of these different examples. So the first one is y equals e to the e. Is this an exponential function? Remember, an exponential function is when you have an exponent in terms of x. Well, no. This one here is just simply e to the e. Well, what do I know? E is a number raised to another number. A number raised to a number is simply just one big number. And so if I were to take the derivative of this, I would just get 0 because the derivative of any number is 0. All right, number 2. Y is equal to x squared. Is that an exponential function? No, don't be confused. We have dealt with y equals x squared since the very first, it's probably the first one we talked about taking the derivative of. Y equals x squared is just your normal power function. And so when we take the derivative of that, we know it's just 2x. Okay, so don't get confused. Anytime you see an exponent, don't think of it as an exponential function. All right, the next one. Y equals e to the x squared. This is a classic exponential function because our exponent is in terms of x. And so when we take the derivative of this using our new rules, okay, this is an e to the u. So we copy down e to the u times the derivative of the exponent, 2x. All right, number 4. Y is equal to 2 to the x. Okay, another exponential function because x is in the exponent. But this time our base is a 2, is a constant other than e. So we copy down 2 to the x times the natural log of 2 of the base. All right, number 5, y equals x to the e. So again, don't be fooled. This is very similar to number 2. But some students run into difficulty when trying to just kind of decipher how to take the derivative of this. Well, remember, e is just a number. And so we use our power rules from the very beginning of the year. And we bring down the e in front, and then it's x to the e minus 1. Just like you would have for the example number 2 here, we're doing the exact same thing. We bring the number down in front, we copy down the base, and then we raise it to the 1 less power. All right, last one, number 6, y equals 2 to the ex. Okay, so this again is similar to number 4, but just our exponent gets a little bit more involved. And so when I do the derivative, I copy down 2 to the ex times the derivative of the exponent is e times, because e again is just a number, times the natural log of 2. And once again, just like we've talked about, if I wanted to clean this up, I could by just saying that this is the same as natural log of 2 to the e for that second term. Okay, thanks a lot, guys. Hope that this was a lot of practice for you, and we'll make sure to practice more when you get back to school. Thanks so much.